Hello and welcome to the first part of section 10.7 power series. This is a slightly longer section, so I decided to break it into two parts. What we have done so far is looking at series. A series has values in there. It has numbers, integers, and fractions, and other things if your series has e to some power or pi. Okay, so it has numbers. We're adding up a whole bunch of numbers. The main reason we wanted to look at series, there were two main reasons. First off, this idea of I give you a whole bunch of tests and then I give you a random series and ask you, does this converge? And you have to use your toolkit that we developed. Nice problem solving skills. Lots of good problem solving skills. The other reason, the more practical reason, is to talk about power series. Power series are used very frequently in physics. We're going to use power series to approximate other functions, and we're going to then look at the error estimate. How close is this power series to this function? So let's talk about power series. So first off, with power series, we now move to polynomials. So where a series extended addition from finite to infinite, a power series extends a polynomial of finite degree to infinite degree. So you can view a power series as a polynomial of infinite degree. Definition: what is exactly a power series? A power series is what we are defining. You have a small little thing that we're also defining here. We're defining this about x equals 0. A power series about x equals 0 is a series of the form summation from n equals 0 to infinity of Cn x to the n. So Cn is just the coefficient of x to some power. This is C0 plus C1x plus C2x squared plus ... If we have a power series about x equals 0, then we can also have a power series about x equals any number. So about x equals a. Power series about x equals a is a series of the form summation from n equals 0 to infinity of Cn x minus a to the n. So that is C0 plus C1 x minus a plus C2 x minus a squared plus ... And notice this power series about x equals 0 is really x minus 0, so it's just a special form of a power series about x equals a. Where these are power series where the center a and the coefficients C0, C1, C2, ... are constants. With power series, the main thing we want to know is for what values of x will the series converge. So this is really asking, since we're viewing a power series as a polynomial, is we're asking what is the domain of a power series. So we mainly And this is what we're going to look at in this section. For what values of x will the series converge? We're going to look at how we're going to go about finding that. Quick example to kind of illustrate what is a power series, what does it look like, and what do we mean. We can consider the power series. One minus 1/2 times x minus 2 plus 1/4 times x minus 2 squared minus ... plus negative 1/2 to the n x minus 2 to the n plus ... This has center A equaling 2, and it has coefficients C0 equals 1, C1 equals negative 1/2, C2 equals 1/4, and etc. So we can write this power series as the summation from n equals 0 to infinity of negative 1/2 to the n times x minus 2 to the n, which we can also write as the summation from n equals 0 to infinity of 2 minus x over 2 to the n. Just combine the negative 1/2 and the x minus 2, and I threw the negative sign in by rearranging into the x minus 2. So then what does this series look like? This series looks geometric. With r equaling 2 minus x over 2. And we know stuff about geometric series. We know that geometric series converge when the absolute value of r is less than 1. So we're going to use this to solve for x to see when this series will converge. So solve this for x. The absolute value of r is less than 1. This is the same thing since we said r is 2 minus x over 2, as absolute value of 2 minus x over 2 has to be less than 1. Multiply both sides by 2. You get absolute value of 2 minus x is less than 2. Decompose the absolute value sign. That means negative 2 is less than 2 minus x is less than 2. Subtract 2 from all three of these. We get negative 4 is less than negative x is less than 0. Multiply by a negative sign, but remember, when you do that, you have to switch the order or the direction of the inequality. So this series converges when x is between 0 and 4. Okay, let's do another example. So the idea with these is we're going to use pre-existing tests, and then you're going to get an inequality involving x, and you want to solve that inequality. Sometimes you don't get an inequality, so consider the example, where does the summation of x to the n over n factorial converge? So we're going to want to perform some tests to determine when this series converges. This is not geometric or a p-series, so we're not going to use those. We have this n factorial in the bottom. Whenever you see a factorial, you should think ratio test. So we're going to use a ratio test. So we have the limit as n goes to infinity of the absolute value of the n plus first term, x to the n plus 1 over n plus 1 factorial, divided by or multiplied by the reciprocal of the nth term, n factorial over x to the n. This is the limit as n goes to infinity of the absolute value of arrange the like terms and pull out, or I don't remember what term I said, but decompose the factorial to get common factorials. The n factorial and the n factorial cancel, x to the n and the n and the exponent will cancel. So we are left with the limit as n goes to infinity of the absolute value of x over n plus 1. And for whatever value x we choose, this will be 0, which with the ratio test, all we care about is the fact that that is less than 1. Note that we didn't care what the value of x was, because x is going to be, you can only pick one value for x. So you can't say, well, let x be n, and then this limit will be equal to 1. It has to be a constant when you choose what value x is. So this series converges absolutely for all choices of x. So we say for all x in the real numbers. So we saw an example of where you get a finite region of where x can be to make the series converge. And we also saw an example where x could be anything. So the next question is, will a series always converge? Can we come up with a series that does not converge for any x? So consider this example. Where does the summation from n equals 0 to infinity of n factorial x to the n converge? So when we go about this, again, we have a factorial, so we use the ratio test. But before we do that, let's look at this series. We have n factorial, which is growing super large as the coefficient, always multiplied by x to the n. We're not dividing by anything. We're just going to keep adding on n factorial, just adding on very large values. So we expect the series to diverge for all x. Well, let's see what we get. The ratio test, we have the limit as n goes to infinity of the absolute value of n plus 1 factorial times x to the n plus 1 divided by n factorial x to the n. We've done this enough times, I skipped a step or two there. This is the limit as n goes to infinity of the absolute value. Deconstruct the factorial to pull out that n plus 1. That n plus 1 will cancel, or the n factorial that is left over will cancel. And then we also get a power of x. As n grows, this will go off to infinity. Really, we should say plus or minus infinity, depending on what value of x is. If x is negative, it's going to tend to negative infinity. If x is positive, it'll tend to positive infinity. But what if x is not positive or negative? What if x is 0? If x is 0, then we have the summation of 0, which equals 0. This converges. So this series, I made a boo-boo. We have n factorial times 0 to the n for n equals 0 to infinity. I forgot about the first term. When n equals 0, we have 0 factorial times 1, which is 1. So this series diverges for all x except where x equals 0. So this is the only time that it will converge. And for those of you paying attention at home, my correction of my mistake was actually a mistake, because 0 to the 0 is indeterminate, and you actually do get 0. Oops. But it doesn't actually matter what it is. It's just the fact that it's going to converge. And this leads us to this fun fact. Not really a fun fact, it is fun, but this is just a fact that we will observe. There is always at least one point for which the power series converges. As we saw above. Looking at the above, this was x equals 0 because we just had x to the n. But remember that a power series can be centered at other things, other points. So we say that it converges for x equals a, and that's on a, which is the center. All right, so we've done some examples. I'm going to give you a few theorems that will build up to the method for finding where a power series converges. Because we saw a few examples, but let's write down an official method. First off, we have the convergence theorem for power series. Convergence theorem for power series says if the series an x to the n, power series, if this converges at x equals c, which is not 0, then it converges absolutely for all x with the absolute value of x less than c. Also, if it diverges at x equals d, then it diverges for all x with the absolute value of x bigger than the absolute value of d. Notice this is not saying, so if it converges at x equals c, then it does converge absolutely for all x with the absolute value of x less than c, but that does not say that it diverges everywhere else. We just know that we're going to get some interval here. So this theorem, along with the previous examples, gives way to the following. So, the radius of convergence of a power series. Okay, the convergence of the series summation of Cn times x minus a to the n is described by one of either it is described by there is a positive number r such that the series diverges for x with the absolute value of x minus a bigger than r, but it converges absolutely for x with the absolute value of x minus a less than r. And then we have the series may or may not converge at x minus a equals r. May or may not converge at the endpoints. This comes straight from the previous theorem. We said that if it converges absolutely at some point, then it converges on an interval. And that's all we're saying here, where it converges on this interval, x minus a is less than r. Okay, if it's not described by that, then we know that it could be described by the series converges absolutely for all x. In this case, we would say r is infinity. We saw this in the second example we did, x to the n divided by n factorial. If it doesn't satisfy either 1 or 2, then we know that the series converges only at x equals a. And we would say that r equals 0 here. And this is from that last example that we did. So knowing that we have, before I say that, definitions. We define r to be the radius of convergence. And the interval of radius r centered at x equals a is called the interval of convergence. Right, so the method for testing a power series for convergence step number 1, we're going to use the ratio or the root test. Now I'm also going to put in parentheses, or the geometric test if applicable, to find the interval where the series converges absolutely. So that would be the absolute value of x minus a is less than r. Or we might get, if you were to decompose the absolute value, negative r is less than x minus a is less than r. Step number 2, after you do that, test the endpoints. You're testing them for convergence. Endpoints in this case would be x equals a plus or minus r. And then step 3, if the interval of convergence, I forgot the of. If the interval of convergence is the absolute value of x minus a is less than r, then we know that the series diverges elsewhere. It diverges for the absolute value of x minus a is bigger than r, and we know that by the nth term test for divergence. So let's do an example and then call it a day. So find the interval of convergence. for the summation from n equals 1 to infinity of x to the n divided by n to the 3 halves times 3 to the n. Solution, we're going to use the ratio test. I prefer the ratio test. You could probably get away with the the root test. I just prefer the ratio test. So we have the limit as n goes to infinity of the absolute value of the n plus first term as x to the n plus 1 divided by n plus 1 to the 3 halves times 3 to the n plus 1 times the reciprocal of the nth term, n to the 3 halves, 3 to the n divided by x to the n. Reduce, you get the limit as n goes to infinity of the absolute value. We have an x. We have n to the 3 halves divided by 3 times n plus 1 to the 3 halves. Well, this is the absolute value of x divided by 3 times the limit as n goes to infinity of n divided by n plus 1 to the 3 halves. Bring the limit inside. You see that that limit is 1. Raise it to the 3 halves, and we get the absolute value of x is less than 3. So we know that the series converges absolutely for the absolute value of x divided by 3 is less than 1 because of the root test. Not root test, ratio test. Okay, decompose this inequality, multiply by 3. We get the absolute value of x is less than 3. And that means negative 3 is less than x is less than 3. We now need to test the endpoints. The endpoints would be 3 and negative 3. So when x equals 3, that is the summation of 3 to the n divided by n to the 3 halves times 3 to the n. The 3 to the n's cancel. And we know that this converges because it's a p-test, p-series. So that means we are going to now include 3 in our interval of convergence. We now need to test x equals negative 3. In this case, we have the sum of negative 3 to the n over n to the 3 halves, 3 to the n. Well, this is the summation of negative 1 to the n divided by n to the 3 halves. And this also converges because this is an alternating p-series. So we also include the negative 3. So the interval of convergence is negative 3 to 3, inclusive. And that finishes the first part of this section. The next part of this section is we're going to see how power series interact.